Okay, so welcome to this next video in which we are discussing the aldose monosaccharides. So we've now seen the structure of 8 aldohexoses, and of course really there are 16 aldohexoses. We haven't drawn them all out because their names are just the L isomer of the 8 that we've seen, basically. So the 8 that we've seen all have a corresponding L isomer. We then saw we saw 4 aldopentoses, but of course there are really 8 aldopentoses. Each one of these 4 has an L isomer. We saw 2 aldotetroses, but of course there are really 4 aldotetroses because each one of these has an L isomer. And then we did actually talk about the 2 aldotrioses. So that is all of the aldoses. At the moment they are in linear form, and we're about to discuss the cyclization of them, which is the form that you might be more used to seeing them. However, just before we discuss the cyclization of them, let's discuss a last little piece of terminology, which is the terminology epimer. Okay, so epimer means that you are the same structure, but you're only out by a single optical isomerism. Okay, so it's best if I give you an example rather than try and define it. Okay, so mannose and glucose, D-glucose and D-mannose, will be defined to be epimers of one another. Why? Because if we look at their structures, all they differ by is one alcohol group, the optical isomerism in one alcohol group. So in D-glucose, this alcohol group here is coming out of the page towards us. In D-mannose, this alcohol group is going into the page away from us. Okay, so they will be called epimers. So if you're only not equal to one another because of one carbon's silly alcohol group going in opposite directions, then you are said to be epimers. Okay, so D-glucose would not be an epimer of L-mannose, because remember, L-mannose would also have this alcohol group here coming into the page rather than out of the page. Okay, so then it would differ from D-glucose in 2 alcohol groups going in different directions, basically. So if you only differ by one alcohol group going in a different direction, then you are considered an epimer of that molecule. So D-glucose is an epimer of D-mannose, D-mannose is an epimer of D-glucose. They are epimers of one another. Okay, right. You can also add, if you want to be really pedantic, which carbon the epimer is with respect to. So for instance, D-glucose and D-mannose, the alcohol group is different on this second carbon. So remember I said the aldehyde group would also always be called the first carbon. So this is the second carbon. Okay, so you could say that D-glucose and D-mannose are epimers with respect to the second carbon. Okay, right. So that's just a little bit of terminology that people like to use. So let's now talk about the cyclization of the aldohexoses and also the aldopentoses. We'll have a look at those as well. Okay, so how does this work? Well, basically this works because alcohols and aldehydes can react with one another, and what's going to happen is the alcohol group on the 5th carbon of aldohexoses, or to be more general, because we're also going to talk about aldopentoses, the penultimate carbon, so the one before the last carbon. Okay, it will either be the 5th carbon if we're talking about an aldohexose, or it will be the 4th carbon if we're talking about an aldopentose. Okay, and the aldopentose that we'll be specifically talking about is ribose. Right, this alcohol group on this penultimate carbon is going to it's going to react with the aldehyde group over here. Okay, and that's going to be able to produce the cyclization of the structure. So let me discuss this reaction with you before we actually look at how these monosaccharides are going to cyclize. Okay, so basically if we have an alcohol group here, so this is an alcohol, so I'm just putting an R there to denote it could be anything, basically. It's an R group, an arbitrary group. Okay, and we're going to add on an aldehyde. So here is our aldehyde. So this is the aldehyde group, and again, R prime just denotes some other arbitrary group. So this is the aldehyde. Then basically these two can react, and what will happen is they will produce something that is known as a hemiacetal. Okay, so they're going to produce what's known as a hemiacetal. So let me explain what is going to happen. Now, I'm not going to give you a electronic flow diagram where I actually show you exactly where the electrons move. I'm just going to give you the sort of cut to the chase story, basically. I'm going to show you what happens. Basically, you're going to split one of these bonds between the carbon and the oxygen. And for the basis of understanding this, we can imagine that one of the electrons in this second of the two bonds is going to go back to the oxygen and the other will go back to the carbon. So remember, in each covalent bond there are two electrons involved, one from each of the components of the bond. So one of the electrons will be from the carbon, one from the oxygen. Imagine that you give the oxygen's electron back to the oxygen and the carbon's electron back to the carbon. This is just for the basis of understanding. Of course, this probably isn't the way it occurs. In fact, I'm absolutely sure this isn't the way it occurs, but it will help you to understand at least. All I'm going to do is basically show you how the number of electrons on one side adds up to the number of electrons on the other. Everything adds up, basically, is all I'm going to show you. Now, what you're going to do here is you're going to break the bond between the oxygen and the hydrogen. Now again, this is a covalent bond, so there is an electron from the oxygen and there is an electron from the carbon. Again, imagine splitting it by homolytic fission, okay, and giving one of the electrons back to the hydrogen and one back to the oxygen. Of course, again, this isn't what will actually happen. Right, now, this hydrogen has a free electron, this oxygen has a free electron, this oxygen has a free electron, and this carbon also has a free electron. And I do apologise, I've drawn a carboxylic acid group here. This is going terribly. I've told you that mannose was called maltose earlier, and now I've put an alcohol group where I wanted a hydrogen. This is the aldehyde group, okay? Now, that wasn't necessary, however. That's not going to play any part in my little storyline, okay? So, basically, we're going to bind this oxygen with this carbon. So this oxygen has a free electron, and this carbon has a free electron. We're going to bind those together. So let me now try and show this. So here is the aldehyde again. Here now is this oxygen, which is singly bonded at the moment. This carbon has a free electron, so we're going to bind that with this oxygen from here, which also has a free electron, like so. Now, the hydrogen of the aldehyde group is still attached to the carbon, but now we have a hydrogen with a free electron and an oxygen with a free electron, so we're going to stick the hydrogen and the oxygen together to form a covalent bond. So that is a sort of everything on this side adds up to everything on this side kind of explanation. It is not supposed to be an electronic flow mechanism. Okay, so this is what you're going to produce. This is called a hemiacetal. So this is what you're going to do in the case of these sugars to cyclize them. Okay, so let's show this with an example. Let's do it for D-glucose, okay? So the archetypal example, the one that everyone cares about. So let's take this molecule, and firstly let's have a look at its linear structure, and then let's see how we can cyclize it, basically. Okay, so let's firstly draw out its 3D structure, because we never actually did draw out its 3D structure. So here is the carbonyl group of the aldehyde group, okay? Then we'll have the second carbon here, the third carbon here, the fourth carbon here, the fifth carbon here, and then the sixth carbon, which will then have an alcohol group off here. Right, okay, so I'm sorry this is sort of squashing everything on. Okay, so then of this fifth carbon here, the alcohol group is, remember, coming out of the page towards us because it's D-glucose we're talking about here. Okay, and this alcohol group here also comes out of the page towards us, so this is coming out of the page towards us here. Okay, the alcohol group of this third carbon is going into the page away from us, so here is this one, and the alcohol group of this second carbon is coming out of the page towards us, so here is the alcohol group of the second carbon here. Okay, so this is the structure of D-glucose, basically. And when people say D-glucose, this really should be what they mean. Of course, people often mean the cyclized version of D-glucose, but really the linear form is what D-glucose is. Okay, the cyclized form has its own special name, and I'll show you that in a moment. So, also note that when you bind an alcohol group with the aldehyde, the hemiacetal uses absolutely every single atom from the two constituent molecules that you started off with. So there's no waste, there's no byproduct, basically. You only produce this. So what now is going to happen? So the normal structure, the structure people tend to draw when they draw glucose is this. And I'm going to show you now how you get this by undergoing a reaction just like this with this molecule. Okay, so they draw this 6-membered ring here. Okay, and then you have up here a methyl group coming off, which then has an alcohol group coming off up here. Okay, so let me put this alcohol group. This structure here is analogous, okay, well, it's the same thing as this structure here. Okay, so what you are going to do is you're going to bind this alcohol group to the aldehyde group and form a hemiacetal, just like you did with the arbitrary alcohol and the aldehyde. And the hemiacetal has this oxygen linking the carbon of the aldehyde, which is now down here, okay, with the structure of the alcohol, which is over here, basically. This R here is analogous to over here, okay. This structure in orange here, this carbon here in orange, is analogous to this carbon over here. And by the way, the carbon of the aldehyde, okay, here, this has a special name. This is known as the anomeric carbon. Okay, so this orange carbon that I've just highlighted, this is then called the anomeric carbon. Okay, so this is the anomeric carbon. Now, whenever you use D-glucose, where you have this alcohol group coming out of the page towards us, or in fact when you use D-anything, when you use any of these aldohexoses, which are the D isomer, and the alcohol group is coming out of the page towards us, then the this final pink group here, the methylene group with the alcohol group coming off, this will be coming out of the page towards you. So I can already say that this is the D isomer, basically, because this group is coming out of the page towards us. If instead I used L-glucose, then the alcohol group here originally would have been going into the page away from us, and that would overall result in this going into the page away from us. Okay, so this is going to be the D-glucose version. Okay, now let me just give you the full name of this already, so that I don't think I should hide it from you right until the end. So the cyclized version of D-glucose is known as D-glucopyranose. Okay, so really when you talk about this cyclic structure for glucose, you should say glucopyranose rather than glucose. And this is the D structure because this methylene group with the alcohol group coming off, this is coming out of the page towards us rather than into the page away from us. Okay, right, now let's turn our attention to this next carbon down here. So this carbon here, okay, if I highlight this carbon in turquoise here, this is this carbon here, basically, and its alcohol group is involved over here. Right, so next carbon along, its alcohol group was coming out of the page towards us. Now when you cyclize it like this, everything turns backwards. So this alcohol group that was coming out of the page towards us, it now goes away from us into the page. Okay, like so. Now, next one along down here, this alcohol group was going into the page away from us, but everything's been turned backwards when we cyclized it. So now this alcohol group comes out of the page towards us. Okay, This carbon here, its alcohol group came out of the page towards us, but everything's been turned backwards, so its alcohol group now goes into the page away from us. Now, this carbon here, this is the carbon from the carbonyl group of the aldehyde, okay? So this was the anomeric carbon, and it still is called the anomeric carbon. And basically, it has had stuck onto it from this reaction that we've undergone. The oxygen of the carbonyl group of the aldehyde has now been converted into this alcohol group, so it now has an alcohol group sticking off it. And then the question of whether it comes out of the page towards us or into the page away from us arises. So the question of, does it go into the page or out of the page? Well, basically the answer is that sometimes it will go into the page and sometimes it will come out of the page. Okay, so you get another bit of complexity here, because when you talk about the pyranoses, these cyclized forms, you don't just have to worry about the optical isomerism here, 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 here. Okay, this was the D and this was the glucose. All of these three were handled by the glucose, remember, because there are 8 different combinations of these three, and those will be taken care of by the 8 different aldohexoses. Okay, but now we've got this final new level of optical isomerism. So, if it comes out of the page towards you, this is known as the beta anomer. Okay, so because it's the anomeric carbon, it's known as the beta anomer. And if it goes into the page away from us, this is known as the alpha anomer. Okay, so because the alcohol group can vary, basically, often you'll see people putting a squiggly line like this to denote that it either comes out of the page, i.e. it's either the beta anomer, or it goes into the page and it's the alpha anomer. So this denotes that, you know, the optical isomerism isn't decided, basically. It can either go in or out. Now, if you for certain know which anomer you're talking about, i.e. you specifically mean the alpha anomer, then you can call that molecule alpha D-glucopyranose. Okay, so the alpha tells you the optical isomerism of the first carbon, the D tells you the optical isomerism of this group here, the gluco tells you the optical isomerism of all of these three here. Okay, and then finally the pyranose just tells you that this is a ring structure. Okay, so basically, if we think about how many different structures there are in these pyranoses, okay, so let's think about this. Well, there's a chiral center here, a chiral center here, a chiral center here, a chiral center here, and a chiral center here. So all of them can be in 2 conformations. So that's 2 times 2 times 2 times 2 times 2. That's 2 to the power of 5, which is 32 different combinations. So there are actually 32 different cyclic aldohexoses that you can make, basically. Okay, so that's why you have to list all of this. You have to put alpha D. Alpha tells you the optical isomerism of this one. The D tells you the optical isomerism of this one. The optical isomerism of these three is then coped with by this name here. Okay, right. So this is the structure of alpha D glucopyranose, or it could have been beta D-glucopyranose. So if you wanted to turn it to the L isomer, you take this methylene group with the alcohol group coming off, and instead of having it coming out of the page towards us, it would go into the page away from us. Okay, so that is the structure of a glucopyranose molecule. Okay, so in the next video what we'll do is turn our attention to the structures of mannopyranose and also galactopyranose. So we'll see the cyclic versions of the other two key aldohexoses which are actually within cells. We'll then also see the structure of ribose once it has cyclized. Okay,